Hey guys, it's Smokey out there, and we're going to be doing our lecture on the material. So if you can have your notes out and you can record this information in, you can either do this on a computer and then you can have your iPad out, or I believe you can also do a split screen with this as students have done in the past. So I hope this works out for you. Email me if something's not working. So we're going to go ahead and continue with our information. And we're looking at something called the Coriolis effect. The Coriolis effect is something that deals with what's called the Coriolis force. If you look at the Earth is spinning. So if you're sending a projectile through space, it actually above the Earth, it's not going to be traveling in a straight line. It's actually going to have a slight curvature to it. And we'll do a lab in class, and this will demonstrate that things will definitely have a curvature as they are spinning. And in the northern hemisphere, what you can see is that a projectile is going to be directed to the right. So the red arrow is indicating that the missile is being fired to the north, but because of the curvature of the Earth, or the curvature, but the rotation of the Earth is going to have the pathway be curved off to the right. So the main concept of the Coriolis force is that objects are going to shift the direction to the right in the northern hemisphere. This shifts the winds, but it also shifts the water, and we'll see how this affects the currents as well. We'll go into more details when we're in class, but I want to show you a couple of things. So if you could take a look at the top picture of the Earth, it's focusing on the equator. We'll draw a picture of this later. As the heat comes down, it hits the Earth at the equator. What happens is that light is going to be re-radiated as heat up into the air. So that hot air is going to rise. You can see those red arrows rising at the equator. What happens is that as they rise, they also are going to hit the top of the troposphere, which is the lower layer of our atmosphere, which is where the most of our air is. And it can't continue to go upward, and we're not going to lose air into outer space. So what happens is that air begins to curve upward towards the North Pole. Similarly, if you're in the South Pole or the Southern Hemisphere, the air is going to rise. It's going to get deflected or diverted towards the South Pole. So imagine if you have, again, a stream of water running on top of a countertop. It hits the countertop, it's going to split in two directions. Same thing is happening with the air. The air rises at the equator, it's going to split, and it's going to split towards the North Pole and the South Pole. Now what's going to happen is this air is eventually going to sink at about 30 degrees north. And about 30 degrees north, it's going to sink, and it's going to hit the Earth again. As it hits the Earth, it's going to then split towards the North Pole and the South Pole. What that's going to do is it's going to create this giant, what's called a convection current, which we talked about before. It's a circular current, just like the asthenosphere. So convection currents also occur in our atmosphere. So between 30 degrees north and the equator, we have the net direction of the movement of air is from the north to the south. Okay, now go to the second picture. We're at 30 degrees north towards the equator. If we're traveling from 30 degrees north towards the equator and we're traveling down or south, to the right from that perspective is going to be to the southwest. Okay, so point your finger down, okay, and as you're traveling down from 30 degrees north towards the equator, if you were to turn right, you would be turning towards the southwest. That creates what are called the trade winds. Those are the northeast trade winds, and in the southern hemisphere they're called the southeast trade winds. So let's follow this convection current. The convection current in between 30 and 60 is actually facing to the north, but because it's being deflected to the right, it's going to be traveling to the northeast. Winds are named from the direction they come from. So the trade winds are the northeast trade winds, and these winds are coming from the southwest, but they've dropped to the south. They're actually coming from the west. Those are called the westerlies. And we also have these winds that are coming from on the north and the North Pole. Those are the polar easterlies. So we will cover these in more detail when we are going to go over this more when we return in class. So that is the correlative force, and that's how it is going to affect the winds and how they affect the oceans as well. We'll draw this all in your lecture notes in just a little bit when we come back to class. There's also another current, and this current is called Ekman transport. Now take a look at the wind. The wind is traveling in a particular direction, but because the Coriolis force, it's going to be turning to the right. Now think of the water as thousands upon thousands of miniature layers of water. And what's going to happen is that each layer is going to be affected by what's affecting it from above. So the surface layer is being affected by the wind. The layer underneath that is being affected by the layer up above it. The layer down below that is being affected by what is above it. So the surface layer is going to be affected by the wind, and it's going to be transporting it to the right. But now we have water that's being transported to the right. The layer underneath that is also going to be affected by the Coriolis force, and that is also going to be turned to the right. And then the layer underneath that is also going to be affected by the Coriolis force from the layer above. That's also going to be affected and turned towards the right. So what happens if you take a look at this is each arrow is going to get a little bit smaller because it's not going to have the same effect as the layer up above because of frictional forces are going to slow the velocity and the push of each layer. So each layer will have a slightly lower velocity until your velocity reaches 0 towards the bottom, but it's going in a slightly different direction. It creates this spiral. This is also called an Ekman spiral. However, if you add all the directions of these arrows in which the direction that they're moving, the net direction is going to be 45 degrees to the direction of the wind. So in the northern hemisphere, if your wind is to the north, your Ekman transport, your water direction, your net direction, the total sum direction of all the water is going to be transported 45 degrees to the right in the northern hemisphere, 45 degrees to the left in the southern hemisphere. So that's called Ekman transport. We'll go over more details in class. Here are the surface currents. The surface currents are these wind-driven large circular currents, and these are called gyres. So if you look at the map, you can see that there are these clockwise and counterclockwise currents. In the northern hemisphere, we have these predominant clockwise currents that carry the water. Okay, Atlantic, you see this giant circular current. Okay, northern hemisphere, southern hemisphere. In the Indian Ocean, you also see that current. Again, it's the southern portions of the Pacific, the Atlantic, and the Indian that create that southern ocean, that current that goes around Antarctica. But again, it's because of the circular currents called the gyres. So we have the North Pacific gyre, we have a South Pacific gyre, North Atlantic, etc. And when the water is traveling across the equator, it's going to be warming up. And it's going to hit the continent. For example, it's going to hit the continent of Asia. It's then going to split, and then you'll have a current going to the south. You'll have a current going to the north. Okay, that will carry warm water towards the poles. They lose their heat. That's why off the coast of our coast, our water's cold because it's coming from the North Pole. It's lost a lot of its heat. Now, if you go directly across the continent to the east coast of the United States, what's their temperatures going to be like? Predominantly warmer compared to ours because their water is coming up from the equator. It's losing some heat along the way, but it's going to be a lot warmer at a certain latitude than it's going to be on our coast, the west coast, at the same latitude. So California water is going to be probably around, in San Diego, you could probably get about 72-degree temperatures. If you go all the way across to maybe even the top of Florida, you're going to have water temperatures that are still in the 80s. So it's quite a difference in temperature. So we also have what's called a density current. And find Greenland on the map. Okay, this is where heavy water sinks and it creates a current on the ocean floor. It's a very famous current. It's called the conveyor belt. And this is a very slow moving current in terms of hundreds of years. So what's interesting is that the water off of Greenland, because it's so cold, it becomes very, very dense. And because it's dense, it's going to sink. So this heavy water sinks to the bottom, and that is the push for this whole conveyor belt. I call it the toilet bowl because that's where this water just sort of sinks downward in the middle of the ocean. This water then gets pushed on the bottom of the ocean floor. It travels then towards Antarctica and then hits Antarctica. Then you'll see that it splits. Some of it resurfaces in the Indian Ocean. The majority of it is going to resurface in the Pacific Ocean, where it's going to get warmed. And then again, it'll repeat the process. This goes up, it's more towards the surface, and then it hits Greenland again, and then it's going to go down and repeat the process again. But this is a process of over a couple of hundred years. We'll talk about the significance of that a little bit later. Those are density currents. So here's something interesting. In the Pacific, there's what's called the garbage patch, where the currents sort of create an area where there's a lot of garbage, and it's between Hawaii and Los Angeles. And in the middle of the ocean, you'll find this just giant region of garbage, and the currents will take the garbage from anywhere in the world, and they sort of get stuck here. I have posted a couple of videos for you guys to take a look at, and this shows the effects of the garbage patch. They've done analysis of the garbage patch, and they found out that there's about 20 times the amount of plastic material in the water compared to the biological life. And we're not talking about large plastics like large plastic bottles, but we're also talking about the tiny pieces and fragments that have broken off that actually would go through a net. They've analyzed the water samples. So not only is there large garbage, but there are small pieces of garbage as well. So what does that have an effect on marine life? Well, here's one of them. Birds see something in the ocean, and all of their experience is based upon what they've seen before. If they see something in the ocean, they think it's food, and so they eat it. And this then gets into their digestive tract, and it clogs up their bowels, and they can't process any more food, and as a result, they're going to die because of this. This happens not only birds, but it happens to turtles, it happens to fish, and fish actually would ingest particles like this, but they also ingest the smaller particles that are almost microscopic, and then that goes into their bodies. And who knows what all of that is going to be doing to their bodies as well. What I'd like you to do is to pause this. I'm going to continue going on, but I want you to watch a couple of those videos that I have left for you describing the garbage patch. One other current that we can talk about is called upwelling. And in order to do this, we'll have to draw the coasts of California. We're going to be drawing a top view and a side view, but we'll also be doing this in class as well. But upwelling is driven by offshore or northerly winds in California. In the ocean, currents just aren't moving to the left and to the right. You can have currents that are moving up, which are called upwelling currents. You can also have currents that are going down, and those are called downwelling currents. Upwelling brings lots of nutrients to the surface of the waters, and this is a major cause of what causes these blooms. This is why coastal areas are so productive, because of this upwelling process that brings these nutrients from the deep depths down at the bottom that have sunk down there, and it brings them back up to the surface. And so it naturally fertilizes the water. Downwelling is the opposite. It takes your surface water and it plunges it down towards the bottom. That also can take some of the biological life with it as well, such as phytoplankton as well as zooplankton. We'll draw this. So one other current, we'll end on this last current, and it's rip currents. How are rip currents formed? These are formed by sandbars. So what you can see in the picture is on the bottom is the beach, and then out in towards the ocean, which is towards the top of the picture, we see a sandbar. and water will flow over this. So you can see these very faint arrows. The waves will be breaking over this. Later in the year, we're going to see that these sandbars actually provide a material for the wave to break. Waves come in from the surface of the ocean, and when they hit the bottom of the beach, that's when they're going to break. So they're going to be breaking out over these sandbars. So we have lots of water in this area to the bottom or to the south of the sandbar. What happens is the sandbar can erode, and when that happens, you have all this accumulated water in the bottom part of the picture, and that creates a riptide. All of the water in the area in the bottom part of the picture starts to flood out through the sandbar. So waves continue to rush in and wash out. More water leaves through this eroded area, and then if you get stuck in this rip current, you can get pulled out. And to avoid this, you're supposed to swim sideways. So this is showing the red symbol where you're not supposed to swim against the rip current. You're supposed to swim to the perpendicular to the rip current. So rip currents are caused when sandbars are going to erode and you have more water in one area than the other, and it's going to then rush to make that difference complete. We'll talk about El Nino next time that we're in class. And again, if you have not referred to those videos, please look at them now.